Okay, so let's continue. It's my pleasure to introduce Jason Lotay from the University of Oxford, who will tell us about some remarks on contact Calabi-Yau 7 manifolds.
Thank you very much. Thank you to the organizers for inviting me to this very nice meeting here in Madrid. Yes, so I'd like to discuss two papers related to a particular geometry in 7 dimensions, which is contact Calabi-Yau geometry, which I'll have to say quite a few times in this talk, so I'll abbreviate it to CCY like that. And I should say from the start that this is joint work with Enrique Saerp and Juliet Saavedra. And what I'd like to do is, first of all, explain the setting of what are contact Calabi-Yau 7 manifolds, and then tell you what the results are. And they come in 2 parts. The first part will be about geometric flows, which I will describe. And the second part will be about the heterotic G2 system. And then, if there is time at the end, I hope to discuss some possible questions that I think arise from this study. And I should say from the outset that what I'm going to try to describe will be hopefully as elementary as possible. I encourage you to ask me questions. And even though it's elementary, I think my reason for choosing it is to hopefully try to gain some further insight into both of these topics more generally, and hopefully it will help us to understand both of these areas. So let's begin with the setting. So what is the idea? Well, the idea is that there is a relationship between Calabi-Yau geometry in 6 real dimensions and geometry in 7 dimensions, which is associated with the group G2. And the relationship is not a complicated one, it's just via circle bundles. So on the Calabi-Yau side, we will have real 6-dimensional, complex 3-dimensional manifold. We'll have H. H will be a Ricci flat Kähler-metric, and I'll want the holonomy of that metric be SU3. We will have omega be the Kähler form. There's a 2 form, and it's going to be, of course, closed. And then the final piece of data we'll have here, which I'll call capital Upsilon, because otherwise there's just too many omegas in the game. And this is going to be the holomorphic bottom form. Upsilon is the holomorphic bottom form, which in particular means that it's closed. This is a complex valued form. Okay. So what do we have on the 7-dimensional side? Well, we're going to have circle bundle, as I said, over this Z. And this is going to have a bunch of data on it. So it's going to have G. G is going to be a metric. It's going to have eta is a connection 1 form for the circle bundle. And so then you can write this metric in a very simple form. G is just going to be eta squared plus h. Make sense? And now, where is the G2 bit? So the G2 bit is encoded in a 3 form. So phi is going to be a 3 form, and it's a very particular 3 form, but not difficult. It's built out of eta and the Kähler form, so eta wedge little omega, plus the real part of the holomorphic volume form. So if you've never seen something like this before, the properties that this has is that it has a kind of positivity property. It has a sort of non-degeneracy type condition. It's a stronger non-degeneracy condition than we saw in Marco Zambon's talk yesterday. So you do have the fact that you have an injective map from the tangent space into the 2 forms by contraction with phi, but you have more than that. And in fact, even though it doesn't look like it, phi actually determines G. So actually this gives you back G. So I don't need to tell you G, I just have to tell you phi, and I can recover the metric from that. And that's not so shocking because we know that you can recover the metric in the Calabi-Yau case just from the forms. I don't have to tell you the A. So this is overkill to give you this data, but just so I write it down. And why do I say G2? Well, we'll see that a bit later, but what you can say is if you have a form which at every point looks like this, and you look at all the transformations of the basis of vectors at that point, which keep this presentation, that will be isomorphic to G2. So it's the stabilizer of this form at each point. It's a copy of G2. Now, I've secretly left a little bit of space here in front of each of these, because it's natural to allow a parameter epsilon to appear in the game. And as we know, epsilon is a small number, right? Small. And that's right. So we want to allow this epsilon to go to 0. We want to say, what's going to happen to this geometry, this G2 geometry, as epsilon goes to 0? How is that related to this Calabi-Yau geometry here? Okay. So we don't want to look at any old circle bundles. We want to look at this contact Calabi-Yau case. So what's the sort of motivating example that you should have in mind? Well, my Z will just be the set of points CP4 is the Fermat quintet. You take the sum I to the phi equals 0. Look at that 0 set, then that's a Calabi-Yau. And then what is M going to be? Well, M is suspiciously looking the same. It's the set of points now C5, same condition, and now I intersect it with the 9 sphere. So that's obviously an S1 bundle over Z, right? And what is the good eta that I want to pick? Well, there's a connection one form eta on M such that the eta is the Kähler form, is the Calabi-Yau. So that exists, and so that's the structure that we want to emulate. And so now we can make our definition.
You're going to assume the Gray class is integral.
Yes, exactly. Here's the definition. So M7G eta epsilon is, I'll write it one more time, but this is the last time I'll write it out in full. It's contact Calabi-Yau. Right, from now on. So what do we want? So we want this just Riemannian manifold to be Sasakian. So Sasakian is the odd dimensional version of Kähler. So this is to say that if I look at the easiest way I find to say it is if I take the cone over this and look at the corresponding cone metric, then it's a Kähler. Right? Sasakian means with our contact form eta. So that's our connection, going to be our connection 1 form. And then I want that if I look at the kernel of eta, so that's going to be 6-dimensional, rank 6 thing. I want that this has Calabi-Yau structure. What's the structure going to be? It's going to be H, which is just the restriction of G to E, so the metric to this distribution. Omega will be d of eta, and that indeed will be non-degenerate and closed because of the contact condition. And then our epsilon. So, all right.
Ask you a question.
Please.
Is it correct that this pre-quantization of M of Z omega?
In this case, yeah. In the case that I wrote there, it is.
Not in general.
Not in general. So I mean, it is in. Well, okay. I mean, so okay. Let me make a remark now. So of course, I haven't written any circle bundle here at all. Right?
Right.
I just said it was a 7 manifold, and I said there was this transverse structure that was Calabi-Yau. I didn't say there was a. But in fact, if you ask this to be Calabi-Yau in the sense that I said there, so the holonomy is SU3, then in fact it always will be a circle bundle over a Calabi-Yau 3 orbifold. So it won't necessarily be a manifold, but it will be over an orbifold. So in fact, this always, that's the remark I was just going to make, so I'll make it now. I just did it, I'll write it down. So the remark is, M is a circle bundle over Z, where this is a Calabi-Yau 3 orbifold.
Epsilon is still closed.
Yep. It's Calabi-Yau in the sense that I've said there. The epsilon is closed. Yeah, I'm assuming that. Right? That's part of my definition. But it's a good point. I'm assuming here that the epsilon, this data that I'm giving you is a closed, is a holomorphic volume form on this E.
And M is compact.
I'm not assuming M is compact, but in fact, yeah, you're asking all exactly the right questions because I was just about to make that comment. Let's assume M is compact for simplicity. But actually, almost nothing that I say involves that. The statement that I made had nothing to do with the compactness.
And even though you say contact, it really is for that contact form, right? If you change the contact form, you spoil the condition.
Yes. Yeah. No, that's right. That's
Okay,
right.
good, okay.
Yeah. No, this is part of the data.
So it really is for the geometry of 1 form.
Yes.
Not the contact.
Not the distribution, it's the form. Yeah. The choice of form is important. Yeah.
And how you define Calabi-Yau structure of a distribution? I mean, E is just a.
Yeah, no, I mean, you can. I mean, it's just.
I believe that you can, but did you say what you mean by?
I didn't, but let's just pretend that we all know what it means.
But I guess like point-wise, it's Calabi-Yau, and all the
Yes.
forms involved are closed, right?
Yes, that's it.
So
That's it. You know, at each point, it has this SU3 structure, the restricted metric. If you look at the holonomy of the transverse connection, it's SU3, all that stuff. Is it okay?
Yeah.
Okay.
So like transversely.
Transversely Calabi-Yau. Yeah. So in fact, in the Sasakian community, that's what they call it. They call it just transverse SU3, this same structure. So if you've heard transverse SUN before, in Sasaki joke, that's what we're calling contact Calabi-Yau.
So I also not asking if epsilon is globally closed or
Yeah, epsilon is closed.
globally.
Globally closed.
Yeah, not only on the distribution.
Yeah, just closed. Yeah, it's a form on M which is closed. Yeah. But it's 0 on all the vertical things. So Oh. Okay, so is it all right?
Yeah, because the being zero on the vertical things is new information as well. Okay.
Yes. Yeah. So whenever you, I mean, and also I didn't say anything about G2 there, right? But of course, if you have such a contact Calabi-Yau, you can write down the same formula. Okay, you can write down this is a G2 structure, and then you can take the dual, the Hodge dual. So as I said, the 3 form determines the metric. It actually also determines the orientation as well. So you can take the star and you can work out what it is, and it's just a half omega squared minus eta wedge epsilon.
Can I just ask one more question? Because you mentioned Sasaki is when the cone is scalar.
That's right.
Is here the case when the cone of this one is going to be Calabi-Yau, or is
No.
just
No, that's not it. No, that's not it. Yeah. No, it's a good question. But it's in it. But yeah, you're preempting against something like you may think maybe there should be some natural Calabi-Yau structure in one dimension higher, right? There should be somehow not. Well, maybe there is.
Oh,
yeah, let's see. Maybe there is. Yeah. Maybe there is. Okay. So yeah, but I mean, it makes sense. Right? There should be, but it's not the cone.
Okay,
not the cone. Not the cone. In general. Okay, so we can write this down. So why have I bothered to do that? Well, what you notice is because omega is closed, epsilon is closed, and d eta is little omega. If I take the derivative of star phi, I get 0. So this is what's called a co-closed G2 structure, for the obvious reason because it's co-closed. And what we see is that if we take d of phi, then it's not 0, it's epsilon times omega squared. So in particular, omega squared is exact. Okay, so yeah, so what I want to say now is that we want to look at things in the realm of co-closed G2 structures. We want to study some of the geometry associated with co-closed G2 structures, which appear in quite a lot of different places, and I want to just talk about that now.
But I think by the Hitchin flow, you get this spin 7 autonomy.
Yeah, very good. Yes, exactly. Yeah. Okay, sure. Yeah, so okay, let's say that now. Yeah, sure, absolutely. Let's do it. Yeah, no, it's fine. No, that's why it's good to have a board talk. Then I can just do things in totally the wrong order. It's fine. That's right. So let's say that now because I'm here. Yeah. So the Hitchin flow. The Hitchin flow, which was supposed to make an appearance in about 20 minutes' time, is if I look at ddt of star, so star t phi t is d phi t. So you imagine you have a 1-parameter family of co-closed G2, and they're all co-closed, right? You also have d phi t 0 on interval times 7 manifold. This is called the Hitchin flow for co-closed G2 structures. And what this will give you is a 4-form, which is very simple. It's dt wedge phi t plus star t phi t, which is closed. And it's a spin 7 structure on this 8 manifold. So whenever you have a co-closed G2 structure with some other analytic assumptions, you can then evolve it in this way, and then you will generate on at least some small interval times a 7 manifold, a natural structure on an 8 manifold, a spin 7 structure. And what does this mean? This closed condition mean? This means that the metric associated to this 4-form, so again, this 4-form has a kind of non-degeneracy type property, which means it determines a metric. You can look at the holonomy of that metric, and it's a subgroup of spin 7. So again, you have a Ricci flat metric. It's interval. Okay. Different.
Out of curiosity, I mean, does this flow to both directions in time?
Yes.
And does
Well,
this-
well, I mean, okay. I mean, there's lots of analytic issues. I mean, if you assume it's real analytic initial data, then yes.
it's like Cauchy.
Yeah, it's just Cauchy. But for general smooth initial data, the flow won't exist at all. And or may exist only in one direction. Or,
This spin structure has no torsion at all.
yeah, it's torsion free.
Oh, well.
That's what I
Even
said.
if you start just with the close.
Yeah,
Oh,
yeah. That's the hitch and flow, right? You just
Okay.
start. You say that. Yeah, that's exactly what you've done. I've said this is closed. So as soon as it's closed, that's parallel. That's the only condition I need, and so you actually get torsion free. What time do I have to stop?
I guess that clock like 22.
22. Okay. Yep. That's fine. All right. So,
What one
please,
simple question.
please.
This is very nonlinear in the sense that the star is also determined by the phi, right?
Absolutely, that's a very good point. So often I belabor this point and put a phi here. The notation gets a bit heavy, but it is important to remember that the star is non-linearly determined algebraically. It doesn't involve derivatives, but
Right.
but there is a non-linear relation between phi and star phi that's quite complicated to write down, but it is algebraic.
And that's what you said, that it might not even exist, the flow. You
Oh,
just mentioned.
that's not
That's
related to
pretty-
this. That's just this is not. I mean, this is just some evolution equation, and you just have to ask: is it well posed? Right?
Right.
Does it have the property of being well posed? And as you said, have to differentiate this and whatever.
Uh-huh.
That's right. There is some nonlinearity there, and it turns out it's not well posed.
Oh.
In fact, yeah, that's the point. It's only well posed in the category of real analytic initial data using Cauchy-Kovalevsky, but not in general. So that's a theorem of Robert Bryant. It says he actually cooks up families of initial data for which the flow doesn't exist at all in either direction. But I suppose it's smooth but not real analytic. Okay, so let's move on to the results. And the first set of results is in the setting of geometric flows. So in G2 geometry, there are at least two natural flows, which go by the name, the Laplacian flow, and the slightly uglier name of the Laplacian coflow. And it does what it says on the tin. If I want to evolve my three form phi, I evolve it by the Laplacian of phi. That's what. But this Laplacian, of course, depends on phi. But which Laplacian is this? I mean, depending on which talk you went to, you'll see a different one during this conference. Even switch signs. This is the Hodge Laplacian. So dd star phi plus d star. Now I'm putting the phi to remind you that it depends. It's this. And remember that we're looking at co-closed forms, so we're always assuming that d star phi. And so this is a flow introduced by Robert Bryant. There's another flow here, which is now for the four form, so for the Hodge dual, and it's the same thing. You look at the Laplacian with respect to, if you like, star phi, and now we could write the same thing plus d star phi plus another term, but remember we're restricting ourselves to co-closed things, so there isn't another term. That's not there. It's just this one. You may say to me, why didn't you do the same thing here? Because look, there's a d star phi there, isn't there? Shouldn't I throw that away? That's a very good thing, but the problem is that unlike the D condition, which is a linear condition, so the co-closed condition is linear on star phi, but it's non-linear on phi. It's actually not clear that the co-closed condition is even preserved by this flow. It looks like I should be able to just throw that one away and it always stays co-closed, right? In fact, it should be co-exact, it should move in co-exact directions, but that's actually not known. And in fact, it might be false. it might be the case that it instantly moves it out of the co-closed regime. So I'll keep it there. So why do you care about these? I mean, you can write them down, sure, but what's the point? Well, the point is that the critical points of both of these flows are the G2 structures, these three forms, these non-degenerate three forms, which are closed and co-closed, which means that if I look at the holonomy of the metric that they define, it's contained in G2. So you're going to get yourself a Ricci flat metric in 7 dimensions. And that's pretty cool because they're hard to find. So that's a great thing to be able to do. So that's nice. Of course, there are many flows that you could write down. You could just cook up anything that has this condition, but why is there some more reason to like these over others? Well, the Laplacian coflow is equal to the gradient flow of the Hitchin volume functional on the cohomology class of star phi. So that's a bit small, but what it says is, if I look at this, so if I look at this flow, I'm going to stay in a fixed cohomology class for star phi because I'm moving in exact directions. So the flow is actually on this class. I can then say, what is the volume of the induced metric, volume of the whole manifold of the induced metric for each of these star phis? And that's called the Hitchin volume functional. It's just the volume of the metric this induces. And then you see that this flow is exactly the gradient flow for that volume. So it's the fastest direction to increase the volume. It's not the negative gradient flow, it's the gradient flow. So it's increasing the volume as quickly as possible. And you can show that the critical points of the Hitchin volume are exactly the closed and co-closed G2 structures, and they are maxima. They are stable critical points modulo diffeomorphism. So the second variation is negative also, it's non-positive, and 0 only in the direction of the diffeomorphisms. So you're doing a gradient flow where the critical points are all maxima. That's good, right? It seems like that's a good thing to do. So I think hopefully you're convinced that maybe this thing is good. This one has exactly the same property, but you just switch everything around. The Laplacian flow is the gradient flow of Hitchin volume on the cohomology class of phi when it's closed. Right? So this is a good thing to study in the closed case. And there's lots of theory now, analytic theory that shows it's a good thing. This one, although it's nice from this point of view, has all these nice formal properties, analytically it's hopeless. At the moment, we can't even prove that this flow exists for a short time. We don't even know it's well posed yet. Okay. So that's another reason why I think, and we don't know this one's well posed either outside of the closed setting. There's another reason why we thought it might be a nice idea to study these flows in this simple setting and just say, what happens? Does it not exist? What's going on? What do they do? Okay, and so what is the result?
Just to be clear, the co-flow is something that you define on 4 forms. Even though you write star phi, you really mean just the 4 form, right?
Yeah. So I do that because I don't want to write psi or something. People will call it psi, and it gets confusing. It is a flow on 4 forms. Yeah, and so there is a slight, there's a slight subtlety because phi determines the metric and the orientation, but star phi doesn't because it's a 4 form, right? So even, so it doesn't notice the orientation. So that's a bit of a pain, but it's a flow. So if you just pick an initial orientation, that's preserved. It's fine. So it's okay, actually.
If I assume that I'm in this circle bundle situation, is it possible to write down what is this Hitchin volume functional because of the Calabi-Yau?
Well, it's not equal to it. Yes, that's right. Yeah, you can. Well, I'm going to say what happens, but yes, it is. Yeah, you can, yeah. So what is the result? Well, so suppose we have our M7 G eta epsilon is our contact Calabi-Yau. And suppose our initial condition is the one that we've been writing down, or the Q. And then what happens? So then the Laplacian flow starting at this initial 3 form exists, but has finite time singularity times 1/8 epsilon squared. Doesn't really matter what it is. It's some finite time that depends on epsilon. So as I make epsilon, but the point is, if I make epsilon smaller and smaller, it exists for longer and longer. The closer I am to the Calabi-Yau, the longer and longer this thing exists. But it always blows up at some finite time. And the Laplacian coflow, on the other hand, exists for all time. That's different, right? Exists for all time, but has an infinite time singularity. Meaning it doesn't converge to some magic G2 manifold we never heard of before. It's not converging. And in both cases, if you look at the Hitchin volume, if you look at the volume of GT, it goes to infinity. Singularity. Whether that's at the infinite time or the finite time. That's what's happening. The volume is exploding, which is sort of what you'd expect, because you would hope, I mean, this is very naive, but you might hope if there was some volume bound somehow on this space, and you've got some gradient flow, it could fail to be proper, that could happen, but you'd like to think under good situations, it would somehow converge to some critical point. But this, there's no hope. I mean, the volume is going to infinity, so it can just escape from that, from the class completely.
So in the second case, that implies there are no G2 structures.
No, I mean, well, you'd love to say, I mean, I'm only starting from that one, right? So there's none that I can connect, right? But yeah, it doesn't prove that there are none at all, but that's exactly the question that you might ask. Like, you know, it's likely, or I don't know, I mean, there's nothing that tells me, there is nothing that I know of that says that this 7 manifold cannot have
but like these metrics that you're getting, they all have S1 symmetry, right?
So they could never be torsion free. I mean, they couldn't have holonomy G2.
Exactly, and the flow preserves that S1 symmetry.
Absolutely. Yeah. Okay. Yeah. So it could never be holonomy G2, but it could have been reduced, right? It could be holonomy strictly contained in G2. It couldn't have holonomy equal to G2.
No, but if it's contained in G2, it would be what?
SU3.
That's okay.
And it wouldn't happen. I mean, it wouldn't happen. It would split into S1 times Calabi-Yau, which it can't be. But there's nothing that tells me that that particular 7 manifold cannot have the torsion-free G2 structure. There is nothing that tells me that. But it's suggestive, maybe, that it probably doesn't, but we don't know.
Are you using anything on the topology of M7 or
nothing? This is just general. And well, since I'm here, so the proof is very straightforward. All you do is you can literally write down the flow. So you can actually just solve it. So the proof is that you actually just solve the flow using an ansatz. So what you do is you say, well, let's suppose that phi t happens to be of the form, let's see if I can get this right there, ft ht squared eta wedge epsilon plus ht cubed. Okay, and you can write down star phi as well. Actually, let me do it. So star phi is 1/2 ht to the 4 squared minus ft ht cubed. Okay, so you write down this ansatz. So this is your guess as to what, I mean, let's not worry about the powers. I mean, it's just the obvious thing to put in once you've played with this enough. It's the only thing we should do.
HTR functions.
They're just functions, yeah. So the point is these are functions. I'm just putting t, it's not the derivative with respect to t. Right? Some people, it's not derivative, I mean, it's just literally, it only depends on t and nothing else. Right? It's the simplest thing you could guess. It's just, I just want time, only depending on time functions. So I just scale. That's all that I do. They're just functions of time only. And miraculously, or perhaps not so miraculously, you discover that if you compute what is the, so one thing you should, one thing you should notice is that if you write down that ansatz, then they're all co-closed. So you see that d star by t is always 0. If you write that down, oh, I forgot the t. So that's always 0. And what you see is if you compute the Laplacian of phi, t, it's proportional to omega squared. And so that means that, proportional to eta wedge omega. And so that means that this ansatz is preserved because it's only moving in this direction. So only this thing is changing. Whereas if you compute the other one, it's proportional to omega squared. And so it's only moving in this direction. And so this, again, this ansatz is preserved and it becomes an ODE. So then the flow is an ODE system. I mean, ODEs aren't easy, but this one is, and you just solve it. Okay, that's it. That's the proof. Easy, right?
Why do you need to include two functions, right?
Yeah, you do. Right? You do. Yeah, if you try and do it with one function, it doesn't work. The ansatz is not preserved. You have to include two. Yeah. So that's exactly. So what are these functions? I mean, so yeah, let me just explain. So what does GT look like? It's ft squared eta squared plus, or I shouldn't have called it ht. It's ht squared h. It's terrible. But you know, so these FTs scale the different parts of the metric in the transverse one or the circle one. Okay. So let me make some remarks about the do it up here. So we have these two different flows. We have the Laplacian flow and we have the Laplacian coflow. Now, because the Laplacian of phi t is proportional to omega squared, and I said that omega squared was exact, that means the cohomology class of this doesn't change along the flow, which we knew, right? We knew that that's true. So we see that star t phi t is the same as star 0 phi 0. However, if you look at the Laplacian flow now, it's ht cubed that is staying the same because we're only moving in this direction. Ht cubed is constant. That means this is not constant because f is definitely moving. So that says that in general, as long as this is not exact, which is basically never, this will not stay constant. Okay? Star t will not stay constant. In fact, what you find is that if I look at the class, it's something like minus epsilon, 1 minus epsilon squared t to the minus a half star 0 phi 0. Remember, that was the time when the flow explodes. It's 1/8 epsilon squared. And it's not so important, but what's important is that you see, if I only told you how the cohomology class is moving, you would know when the singularity happens. Right? You would know that. And that's the same thing as in Calabi-Yau flow. Right? When you have the Calabi-Yau flow, if you have at least definite C1, then you can tell when the flow will stop existing just from looking at how the class of omega is moving inside the Cala cone. You can just read off what the, I mean, there's nothing like that known, but we can, it's just an observation that we can see it in the same thing in this case, that we can detect the singular time just from this cohomology class.
Do you understand what type of similarities you develop?
Yes, yes, I do. So yes, so that's what I was going to say. So this one, as I say, is a finite time singularity. And what's happening is as you head towards the singular time, this direction is expanding, the circle direction is getting bigger and bigger, and this z direction is contracting. Okay, so that's what's happening. So as you reach the singular time, this circle direction becomes an r. So the whole thing is sort of collapsing to the real line as you head towards the singularity.
So do they both collapse at the same time, or the S1 becomes R before the Z6 becomes?
No, at the same time.
At the same time.
At the same time. Yeah, exactly the same time. This becomes a point, and this one's becoming R. And this, in this case, is the other way around. So this thing expands, and this one contracts. Exactly the opposite behavior, but still the volume goes to infinity in both cases. The volume is still exploding because the rates are such that the total volume is still going to infinity. Yeah.
So at time 0, the Laplacian flow is the class is exact. The class
Yes.
is 0. Or?
No, it's not. It's not 0. It's whatever. Oh, sorry. Maybe I messed up with the epsilon here. It should have been that they're equal at the initial time. Yeah, it's something like this. Sorry. Yeah. They also have to be equal. It didn't have 1 equals 1. Sorry.
And this cohomology control, this doesn't exist in general for Laplacian flow. It's just
No.
the ansatz, right?
Yeah, it's just the ansatz, but it's just an observation. That's all I'm making. Everything I'm doing here is super specific to this specific case. But I'm hoping that something like this might be true. I don't know. It's just a guess, right? Because I mean, we don't even know if the flow is well defined. So I'm not. But it is in this case, and it preserves co-closed, right? Which I didn't know was true in general, but it is true in this case.
Is there a candidate flow for the cohomology class?
Well, I think this is saying you should be able to predict that it's actually an ODE, just like it is in the Calabi-Yau flow, right? There's an ODE that you get, right? That's why you know how it evolves. Is you solve an ODE. We don't know anything like that, but hopefully, it's all speculation. I don't know, but that's my hope. So something like this might be true. And yes, and to answer your question, Mario, yes. So at the singular time, this is what's called a type 1 singularity, or rapidly forming singularity. So those are not known to happen in the Laplacian flow for closed G2 structures. You've never seen that. You've never seen that for a compact thing. But here you do. You see a type 1, finite time type 1 singularity. Here, it's an infinite time singularity. It's what's called type 2b, doesn't really matter, but it's what's called slowly forming. So it's not heading towards something, it's not heading towards, it's just the singularity is going very, very slowly. The sort of rate at which the singularity is forming at infinity is slow. Yeah, but you're still having this sort of dimensional collapse behavior, which is not that surprising. I sort of feel like it's trying to become Calabi-Yau, right? But it can't. That's what it's trying to do. Okay. So let me move on now to the, oh, and there's one more thing I want to say, which it's just because it's here, Hitchin flow. Yeah, so you can say, well, what's this Hitchin flow thing? Does this have anything to do with these flows that I write down? A priori, it should have nothing to do with it. I mean, this is some parabolic PDE. This is something that's not even well posed. But it turns out that the Laplacian coflow and the Hitchin flow are the same up to reparameterization of time. So up to a change of time, these are the same. And you don't just get a spin 7 holonomy. You don't get holonomy spin 7, you get Calabi-Yau. So the space-time track. So in this case, if you look at IT times M7, it's a Calabi-Yau fourfold. So the space-time track of the flow is has a Calabi-Yau structure. So this answers your question. There's the Calabi-Yau
Right, it's just
in one dimension higher.
just not the conical metric.
It's not the conical metric. It's the Hitchkin flow of this thing. So if you take the Hitchkin flow, you will get a Calabi-Yau structure, and that will always happen for any of these contact Calabi-Yaus. If you do the Hitchkin flow, you will. I mean, that's what it says.
This new parameterization is time and isometry as well, or
No.
no? It's really just expanding, right?
Yeah. It's just some ad hoc. You have to write down reparameterization. I mean, that's a totally different flow. It's nothing to do with it. But it's just that they do coincide. Oh, I should say, this is not a new Calabi-Yau metric. This is one that was already known. It's one due to Calabi, in fact. So it said he gave a way to construct on, if you start with, it's much more general, but in particular, if you have a Calabi-Yau threefold, you can build an incomplete Calabi-Yau metric on a disk bundle over the Calabi-Yau, and that's what this is. It's that one. So it's incomplete. It's only defined up to some finite time. Okay. So now I want to talk about the heterotic system. Okay, so since we're going to have a few talks on this, I'm not going to explain where this comes from, mainly because I actually don't know properly, but I'm going to write down what it is. Okay, so what is this heterotic G2 system? Oh, one thing I have to do is I have to recall something. So suppose you have a 7-manifold with one of these G2 forms that's co-closed. And suppose you have A is a connection on some bundle over this 7-manifold. Then there's the notion of A is a G2 instanton. If and only if I look at the curvature of the connection, then it's kind of anti-self-dual. It's kind of an ASD instanton. Of course, that equation does not make sense because this is a 2 form and this is a 5 form, so there's no chance it's going to be true. But 5 minus 2 is 3, so I can put phi in there, and it works. Okay. So that's the G2 instanton condition. And these are very nice. They're minimizers of the Yang-Mills functional. They're very nice connections. Now this is true, but this is slightly unwieldy to work with. It's actually equivalent to asking that this is true. So if you take the 2 form of curvature and you wedge it with star phi and you get 0, that's actually the same condition as the G2 condition. This is one that's easier to work with. This is the one that's obviously nicer because it makes you think of anti-self-duality, but this is the one that's computationally more efficient. Okay, so that's the G2 instanton thing. Now I want to define what it is to have a solution to the heterotic G2 system. So you need, it's a mixture of a statement about a G2 structure, but also connections on your on some bundles over your 7-manifold. So definition. So we have M7 phi, where phi is a G2 structure. A, some connection on some bundle E over M. Nabla is going to be a connection on Tm. And alpha prime is going to be a positive number. Okay, and so then we say that phi pair AE nabla alpha prime is a solution of the heterotic G2 system. Sometimes this is also called the G2 Holz-Strominger system, but I'm not going to do that. I'm just going to call it one name and stick with it. Heterotic G2 system if d star phi is 0. So that's good. That's the co-closed thing that I've been talking about. A and nabla G2 instantons. We have these two different G2 instantons, one on the tangent bundle, one on this auxiliary bundle E. Now, here, so strictly speaking, I could have allowed a conformal change here, but I'm assuming that's this dilaton thing, but I'm assuming that's 0, just for simplicity, because that's a conformal transformation. I'll get rid of that. So that's what people know. Now, when you have this, whenever you have a co-closed G2 structure, then you can always write d phi as some multiple of star phi minus star of some 3-form H. So H is the 3-form flux. And it has this sort of orthogonality relations. If you wedge it with phi, you wedge it with star phi, you get 0. So it's just a way to pin it down, which one it is. All right. So at the moment, this is highly underdetermined. I mean, you know, there's way too many. I mean, at the moment, there's nothing to do with the phi and A and nabla are kind of very weakly coupled. You know? But then there's this final condition, which is the anomaly-free condition or heterotic Bianchi identity. Says the following. It says if I look at D of H, okay, that's some 4-form, and you may have also noticed alpha prime didn't make an appearance yet in the story. Here it is. Alpha prime over 4, the trace of FA squared minus the trace F nabla squared. And some people write R nabla squared, but I'm going to just write F. Okay. So that's the system. Any questions about the system of equations?
Does it imply like a supergravity?
I think it's well, up to this dilaton thing, it is like a consequence of the supergravity when you reduce dimensions. It's a dimensional reduction of these heterotic string theory equations.
The reaching tensor
of the what, sorry?
the metric determined by phi.
What's the metric determined by?
No, so what is the reaching tensor of the metric determined by?
Oh,
The answer is yes.
something.
It's something.
It's something. I mean, it's some mess. Yeah. But it's just they have this relation between them. In this, I mean, on the face of it, this looks pretty wild. But actually, as I'm not sure if this is what Zenya's going to talk about. But in fact, this is actually a very rigid system. In fact, so it looks like there's lots of freedom here to jiggle things around. Like, you know, this coupling is kind of strained at some quite high order. You know, so then, you know, this is already a first derivative of phi. This is a second derivative of phi, and you're asking for this is kind of. But it turns out that this is actually a very rigid system of equations.
I think the question by Jeff is whether a solution of this heterotic G2 system satisfies also this equation of motion.
I see.
Okay.
Which I think is not the case, right? It's only up to alpha prime.
No, it's the case.
Oh, it is the case.
Yeah,
Oh,
it's true.
It's true. Oh, it's true. Okay, great.
And then the Ricci tensor is prescribed by the Einstein equation. So you can read the Ricci tensor from that equation.
From which one?
Not from the Einstein equation of heterotic supergravity.
Oh, I see.
It gives you a formula.
Cool. Okay, so what can we do? I mean, so our goal was, well, you see these equations, I mean, they're quite hard to solve. So, and we don't really know much about getting solutions. So our idea was, can we find solutions in this contact Calabi-Yau setting? So that was the goal. And the theorem is the following. So if M7 G beta upsilon is contact Calabi-Yau, then for all alpha prime positive, there exists so the E is the kernel of the contact form. It's the thing that I called E before. It's the same one. Nabla. So it's not a solution. I'll say that right now. Is an approximate solution, which I'll explain in what sense, to heterotic G2 system. Where? So phi is our old friend, usual one, right? Epsilon, beta, which you've seen it so many times. That one. A is a G2 instanton. The anomaly is satisfied. DH is non-zero and anomaly satisfied. But we cannot get this thing to be a G2 instanton. We can't get the Nabla connection to be a G2 instanton. But what we can do is we can make it as small as we like. We can make it order of alpha prime squared. Remember that, so here alpha prime is supposed to be small. I mean, I said alpha prime, we're all about alpha prime positive, it's true, but we're really thinking about alpha prime going to 0 or alpha prime being very small. So this is all true, and of course there's nothing, actually, I put alpha prime squared, but there's nothing special about squared. I can put any power, positive power I like here. I can make it alpha prime to the k for any k positive I want. So I can make it arbitrarily close to any order in alpha prime. And then,
And how do you do that actually? How do you do that? How do you get to become high order in alpha prime?
Yeah, okay, I'll explain it a bit.
Sure.
But yeah, I mean, I have to do something, right? But yeah, I'll explain. So then this epsilon depends on alpha prime. So this is the key. So that's why I kept putting this epsilon in there in this circle thing. And it's not going to be a shock to you if I tell you that this function goes to 0 as alpha prime goes to 0. Right? You have to collapse the circles in the fibers if you want to get closer and closer to a solution. So again, it's trying to become Calabi-Yau and a kind of trivial solution to the heterotic G2 system, which is just a product of the Calabi-Yau solution. Is it clear? Or are there questions?
I thought in physics somehow the structure of your space-time was fixed, and you could not let it depend on the alpha prime parameter that appears in the expansion.
That's true, but I'm just saying whatever alpha prime is, I can find something, and then if I wanted to order alpha prime to the 1 million, I could do that.
Yeah, but you're putting the alpha prime in the phi that determines the metric. Like,
Sure. Yes, but if I know what alpha prime is, then I can spit that out. But yes, I understand your complaint. It's not a solution.
The physicists should be complaining.
No. They can complain, absolutely. I think what I'm trying to say is that I suspect there is no solution. But what I'm also trying to say is that if you're the kind of person who's sort of looking numerically for solutions to this, you might run into problems because you can get things that are arbitrarily close to solutions which are not solutions.
But like your starting point is kind of a Calabi-Yau threefold. So if you take the torus, because then you have a whole bunch of flat things going on as well, right?
Yes, yeah. So then there might be some hope. Yeah, but yeah, and we're looking at that.
boring.
No. No, I mean, I think if you just have this single circle, it looks like you can't do it. That's my suspicion. But it's only it's within this ansatz, right? So I'm not claiming there's no solution on this space ever. And so let me just say very briefly, what's the key idea in the key idea in the proof. So the key idea is, well, the key ideas in the proof, let's say. So A is just going to be the transverse Calabi-Yau connection. So remember, we have this transverse structure, and we can take that connection, and remember we have a base, right? We have a Calabi-Yau connection, which is just the Levy-Tutor connection of the Calabi-Yau metric on the base orbifold. You can pull that back, and that will be something. And it actually turns out it's a G2 instanton. It's a very simple calculation. Oh, I may as well do it since I'm here. So remember that star phi is a half omega squared this. But A is then Hermitian-Yang-Mills. So that means if I look at FA wedge omega squared, I get 0. And if I look at FA wedge upsilon, I get 0. And so lo and behold, if I wedge with that, I get 0. So it's a G2 instanton. So what is nabla? That's somehow the sort of, that's the key point. So nabla, what we do, I mean, we do various things, but the simplest case is you take it to be this nabla plus connection that we've been seeing over and over, this bismuth connection. But you see, what we can do is we can take the connection not necessarily for the scale epsilon, but for any scale we like. So we do this kind of scale breaking thing. We have phi defined by epsilon, but we can take this connection, which is defined for some other epsilon. Right? And what you can then do is you can take kappa squared to be alpha prime cubed, and epsilon to be, -3, and this to be alpha prime to the 5, or the 2 alpha prime to the 5 or something. And then you see that you get that order alpha prime squared. You can kind of match things up. So you can have the product, going to 0, but one of them is going to infinity. And the other one's going to 0 faster. You can sort of do a mismatch between them. Somehow the key point. So that's how we do it. We sort of use the wrong connection in some sense. I think you'll see a similar trick maybe in materials talk, sort of similar trick in the materials talk later. But anyway, this is sort of the idea that we had, and it works. But I mean, the key point was that we were very keen that we wanted to get the anomaly condition on the nose. We didn't want to get that approximate. We wanted that precise. Right? Really, DH is alpha prime, no corrections, literally that. And that is what we were able to achieve with this, by the expense of not being able to get an exact G2 instanton, but just as close as you like on the tangent bundle. Yep. Yeah. Great. Yeah, you're preempting me. Yeah, absolutely. So remark. We can also use nabla minus. We can also start, but we have to modify it in a similar sort of way, some scale breaking and some other things. But we can also start with the nabla minus connection. We can also start with the Levy-Tutor connection. I mean, once it's kind of true for one, it's kind of true for the others after other modifications. They're more complicated in this case. It's not just scaling. You have to add in some extra terms, but we can also modify. So it's more complicated. It's why I don't write it down. But we can also use the nabla minus connection and still get the anomaly on the nose. Okay, and the last thing I wanted to say, the last question that I wanted to sort of ask is, can we find any conditions on, this pair of phi, AE, nabla alpha prime, which says there is a solution or there isn't a solution? Can we find any obstructions to the existence of solutions? And even a much simpler question is, well, still hard, I think, is can we find any obstructions to the existence of this? Because this is actually our sticking point, right? Finding G2 instantons. There's no thing like stable bundle means you have a G2 instanton. And I cheated, well, I didn't cheat, but I used the fact I know Hermitian-Yang-Mills connections exist. And that's often the way things go, even for Holz-Strominger as well, is you have stable bundles and therefore you have Hermitian-Yang-Mills connection. But we don't know when a bundle admits a G2 instanton or not. And that's actually our main barrier. But even if you do that, suppose that you knew there were, could you find out some other obstructions beyond just having instantons? If you always have instantons and phi's, is there another obstruction coming from the anomaly? I would, maybe not, I don't know. So that's the sort of question. And as I've heard from Mario's, maybe there's a way to interpret this heterotic G2 system in terms of generalized geometry, but that doesn't exist yet. But the Holz-Strominger, the one in one dimension down, does. So maybe there's something in this case too. And with that, I will stop. Thank you very much.
Thank you. Questions or comments?
Yeah, I want to ask if you know of any supersymmetric interpretation of this system in this result in which you have all the solution except for the instanton condition of the nabla.
I personally don't, but
Sorry, what was the question?
the question was, is there an interpretation when you solve everything apart from nabla being a G2 instanton? So it's only approximately G2 instanton. Is there a supersymmetric or physical interpretation?
The problem is not supersymmetry in that condition. The problem is not supersymmetry that will satisfy the equations.
Oh.
So you will have a supersymmetric solution to not that solution.
Yeah,
Did you hear that?
Yeah,
Everybody?
yeah, that's the situation in the Holz-Strominger. Like, this seems like a Holz-Strominger analog a la Yau, in which you don't ask for the connection on the tangent bundle to be an instanton,
Exactly.
but you still retain supersymmetry.
Yes. So that's right. So I mean, if you're not bothered about this, I mean, as you say, and when people look at Holz-Strominger, like Yau and so on, they tend to ignore this. It should be a Hermitian-Yang-Mills on the tangent bundle. They ignore that and say, well, we'll just pick some other thing, like it's churn or something. No, that's fine. I mean, it's fine, but if you do that, you have to solve the anomaly, right?
The equation functions get corrected at alpha 4 alpha prime squared anyway. So
That's true, but I think then you'd also have to satisfy probably the next order in alpha prime and the other equations. I think, So I mean,
this should be happy as long as you're below 4 alpha prime squared.
yeah, that's sort of also why we did this, right? This magic. This thing comes from truncating at some order in alpha prime, and there's then corrections to this at higher order in alpha prime. And so we thought, well, if we can make this order alpha prime squared, that's somehow beyond the regime in which you did the truncation. That's not quite legitimate, but it was sort of, I think, motivated by what you say in physics.
In the case when your Calabi-Yau is a torus.
Yeah, so I ignored that case, but yes, go on.
But like, because then the M7 is going to be a new manifold, and
Yes.
like the computations should be simple.
So then it's been studied as well. So not necessarily just the S1, but you allow everything to move around. You just have nil manifolds. That was done by Marisa Fernandez and Ivanov and Villacampa, maybe. I forget the list of names. Maybe Ugarte. Yeah, Ugarte. Yeah. Okay, so I did remember the names. Good.
Okay.
Yeah. So that there is a paper where they do 7 and 8 actually. I mean 6 and 7. They do the Holz-Strominger and the heterotic G2 system on nil manifolds.
I see. And it was like, it seems like a lot of data because you always have this bundle, like I guess your bundle is very specific because the horizontal distribution, right?
Yeah, well, we did that because we wanted to solve the anomaly. You see, the problem with the anomaly is that to solve this, you have to have a very good understanding of what the relation between FA and F nabla might be. Right? So we wanted to pick an A which we could relate to nabla in some way. And any of these connections, nabla plus, nabla minus, they're very closely connected to A. And so then you can cancel out the terms here and get it to exactly match so that it hits DH.
And I guess you mentioned that some like the starting example is a circle bundle over Calabi-Yau.
Yeah.
But you said you could also get orbifolds.
It's always, it's actually always orbifold unless it's the Fermat-Quintet.
Right. So like, well, what about the orbifolds? Like orbifolds, it's like discrete group singularities or S1 singularities?
No, they're discrete.
Discrete groups.
Yeah, but all of this computation is actually just local.
I see, but like again, in no case you got an example in which that term was 0.
No. I mean, in fact, we actually showed these things can never be.
Oh.
None of these. It doesn't matter. It's not like, in fact, none of these nabla plus, nabla minus, none of them could ever be G2 instantons. So it's not about trying to solve the anomaly as well. We couldn't find a G2 instanton full stop on the tangent bundle.
Oh. Even though, of course, like I was thinking, new manifolds, they have trivial tangent bundle.
Yes.
Somehow the curvature is going to be non-zero.
That's right. Yeah. So we couldn't find one at all. So in fact, that was our only barrier. I mean, we could mess around with this, and starting with nabla minus, nabla plus, all of them, we could make the anomaly work, but we could never get G2 instanton at all. But it was an extra challenge to get G2 instanton to very, very closely. So if I just put nabla plus epsilon, I could have solved the anomaly, but I couldn't have made it close to being a G2 instanton. That's why we did this mismatch thing. So in fact, if you choose just the nabla plus connection, it's very far away from being a G2. In fact, it explodes. It goes further and further away as alpha prime goes to 0. And that's why we did put this kappa in there to counteract.
Yeah, I just wanted to make a comment that this iterative G2 system does have an interpretation in terms of general geometry.
Oh, it does? Okay.
Yeah, you need to consider a transitive current algebra. And then these are solutions of these Killing spinor equations that Luis was talking about.
Oh, okay.
And in particular, they are, if you solve the full thing with nabla at G2 instant, and then you have generalized Ricci flat.
Oh, great. Right. So that's
we wrote this in
fits with what you were asking, Jeff. There's the generalized Ricci flat is secretly, well, not even secretly, I mean, it's known.
Yeah, this is explained in a preprint with Andrew Clark and Carl Fickler.
Ah, yes. Sorry, I've forgotten that. Yeah, that's great.
So there are no more questions or spoilers. Let's